we have been doing a very important algorithm for AI, A-star algorithm. Today in the class, you will implement this also. Now, last time we proved the admissibility of A-star algorithm. And the crux of the proof is the following. Just listen to me very attentively. The crux of the proof is that any time before A-star terminates, okay, there is a node on the open list. Now, one of the important things in your lab today will be the open list and closed list management. We would like to see your code by which you are managing the open list and also the closed list. In the open list, main activity is that nodes enter. And in closed list, the main activity is nodes get transferred from open list to closed list. The nodes which are regenerated, their parent pointers are changed if there is a shorter length path found. This activity will have to be repeated for nodes and their children and grandchildren and grandchildren if the node has gone to the closed list already. Okay. So now with a very simple restriction on the heuristic called monotone restriction, which I'll be covering at some point of time, the heuristic should satisfy triangular inequality. Okay. The heuristic value from a node to the goal node is less than or equal to the heuristic value of the child to go to the goal node and the cost of going from the parent to the child. Okay, the triangular inequality should be satisfied by the heuristic. Now, display style heuristic and Manhattan distance heuristic for 8 puzzle satisfy the triangular inequality, or they satisfy the monotone restriction. Okay, so you don't have to do anything to the closed list if monotone restriction is satisfied. So, so what happens to the open list is that nodes keep coming and their F values are computed. Okay. Now, a very important quantity for us is the F star value, F star S. Okay. F star S is the G star S plus H star S for the start node, which is equal to the cost of the optimal path from start node to the goal node. F star S is the cost of the optimal path from the start node to the goal node. Okay. Now, this is the key point that any time before A star terminates, there is a node on the open list whose F value is less than or equal to F star S. Okay, it has to happen. And physically speaking, there is a node from the optimal path which is in the open list, and all whose ancestors have gone to the closed list. That means for that node, the optimal path from the start node to that node has been found. Okay, so this is the key point. Now you can see that when S is expanded, let's say A, B, C are the children of S. One of A, B, C has to lie on the optimal path to the goal node. One of A, B, C. Okay, so at this point of time, after S has been expanded, there is a node on the open list which is on the optimal path and to which the optimal path from S has been found. That node is, let's say, B. Now, when B is expanded, let's say C, D, E come to the open list. One of these, let's say E, is in the optimal path. It has to be, okay, because the journey is to the optimal path. And on the way to the optimal path, you will pick up nodes which are on the optimal path. If the heuristic is completely intelligent, H equal to H star, then you will not even look at any node for expansion other than the one which is on the optimal path. This is a very directed, narrow search, very efficient search. Okay, so this is the key point, that there is a node from the optimal path always on the open list for you to look at, discover. And the path to that, the optimal path to that node has been found. It is a segment, okay, initial prefix of the optimal path, which is found for that node. Only we do not know that we have found it. Okay, so there are lots of very interesting philosophical angles of A star. You know which node to pick up to go to the optimal path, but you cannot see it due to this is what makes the course AI and not an algorithm course. I know that there is a node in the optimal in the open list which takes me to the optimal path, takes me to the goal following optimal path, but I don't see it, and don't see it because of what? Because of because of yeah, many options, but because of I'm looking for the term, particular term, which is AI relevant. The node which will take me to my goal following optimal path is there on the open list. I do not see it because of my ignorance, philosophically, okay? Because of lack of knowledge. If H was equal to H star, I have complete knowledge about the heuristic, about the heuristic, about the problem, and that takes me to the goal. That takes me to the goal in a very directed manner. And if I am ignorant, H is equal to 0, Dijkstra's algorithm, then there's a beautiful phrase in Hindi, मुझे बहुत भटकना पड़ेगा. Okay, बहुत भटकना पड़ता है. I'll do a lot of useless expansion. Eventually, I'll reach the goal. A star has to terminate finding the goal. Eventually, the optimal path will be found. But बहुत भटकना पड़ेगा उसके पहले. Okay, so there are philosophical angles to A star algorithm, which is why it has remained a pillar of AI. And of course, after going to the lab, you will not philosophize. You will sit down and write Python code. Okay, but remember that there are these beautiful facets of the algorithm. Okay, now because at any point there is a node on the open list whose f value is less than or equal to f star. Okay, the algorithm will have to first of all terminate. Okay, there is a node always whose f value is less than or equal to f star. If it does not terminate, then G value, okay, the G value will keep on increasing for very deep and large graphs. Okay, G value will go on increasing, we'll see. Then after some time, F value will become unbounded. Okay, so that's not possible because there is a node on the open list whose F value is less than or equal to F star. So before F becomes unbounded, this node will be picked up from the optimal path. And you will be again begin journey to the optimal path, to the goal following the optimal path. Okay, and what is the reason why when G, the goal node has been picked up and transferred to closed list, which is the condition for termination with success. There, the path has to be optimal. If it is not optimal, what will happen? If it is not optimal, then the f value of G when it is expanded will be more than f star s. Okay, that's not possible again because there has to be a node on the open list whose f value is less than or equal to f star s. So the path has to be optimal. So A star will terminate, then the path will be optimal. Okay, any question? And I stand corrected. Okay, BFS per se is not guaranteed to give the optimal path. Okay, because BFS counts only the number of edges. It doesn't count the sum of the weights, which is done in Dijkstra actually. So Dijkstra is guaranteed to give optimal path. BFS not. Sorry about it. Okay, so admissibility we have discussed. Okay, now here the first exercise is illuminating. It asks you to prove if the distance of every node from the goal node is known. Distance is known. Okay, then no search is necessary. Here distance means the optimal path. Okay, the distance of the optimal path from any node, the path is not known, but the distance to the goal node is known, which means H is equal to H star. Okay, so prove that then no search is necessary. So see how again that point about Fn less than or equal to F star S is made use of in the proof. So I'm reading the proof. For every node n, Hn is equal to H star n, and the algorithm is A star, because that is the condition for A star algorithm, H less than or equal to H star. The lemma that we have proved so far is that at any time before A star terminates, there is a node M on the open list that has Fm less than or equal to F star S. S is the start node, M is the node on the optimal path, all whose ancestors are in the optimal path are in the closed list. Okay, this we have seen. Now for M equal to GM, for M, GM is equal to G star M, because all its ancestors have gone to the closed list. And hence Fm equal to F star S. Thus at every step, the node with F equal to F star will be picked up, and the journey to the goal will be completely directed and definite with no search at all. Note, when H is equal to H star, F value of any node on the open list can never be less than F star S. Okay, the F value of any node on the open list cannot be less than F star S. Okay, so this is a case of complete knowledge, and which avoids any search at all. And then if the H value for every node overestimates the H star value of the corresponding node by a constant, then the path found need not be costlier than the optimal path by that constant. Okay, let's prove this also. So under the condition of the problem, Hn is less than or equal to H star n plus C. That is given. Now, anytime before the algorithm terminates, there exists on the open list a node M such that Fm is less than or equal to F star S plus C. Okay, that's because Fm is equal to G star M. M's ancestors have gone into the closed list. G star M plus H star M plus H star N. Okay, and H star sorry. Fm is equal to Gm plus Hm. Okay, and Gm has to be equal to G star M. Now Hm is less than or equal to H star M plus C. Okay. The reason is as follows. Let M be the node on the optimal path, all whose ancestors are in the closed list. There has to be such a node. Now Fm equal to Gm plus Hm, G star M plus Hm, less than or equal to G star M plus H star M plus C, which is equal to F star S plus C. Okay. When the goal node G is picked up for expansion, it must be the case that Fg is less than or equal to F star S plus C, which is F star G plus C, because H value and H star value for G by definition is 0. Then Gg is less than or equal to G star G plus C, since Hg equal to H star G equal to 0. Okay, so this proves that the optimal path which is found need not be more than the constant by which the heuristic overestimates H star. Okay, this also you should verify in the lab. Okay, now we'll go to establishing an intuition that better heuristic performs better. So before that, let me try to do. So I'm using ChatGPT and asking it to see if 8 puzzle problem can be solved. Okay. So it is ChatGPT is a large language model. You will get to know more about this if you do an NLP course or a machine learning course which covers these things. So let's see. Okay, I'm asking ChatGPT to solve 8 puzzle problem. Now, ChatGPT must have seen 8 puzzle problem being solved in its training data. Okay, so it must have got many instances of 8 puzzle problem. So maybe it will just retrieve it. I don't know. Okay, so but the key point about such large language models is the instruction you give them. Okay, it is said that we interact with large language models in such that the programming is in natural language. Okay, so let's see. Please solve. Is the screen visible to everybody from the back also? Can you do a thumbs up? Too small. Please solve the 8 puzzle problem. Let's see what it understands. Says it's a classic AI problem. Oh, gives you all information. Okay, so okay, so no lecture is needed. Just go to ChatGPT. Oh, it keeps on giving information. Okay. Suppose I tell, okay, enough. It stops. Oh, no, no. Oh, got it. Let me know if you need further assistance. So, as an NLP researcher, I am amazed where, the distance that you have covered in last 20, 30 years. How far NLP has moved, really? Natural language processing. Okay, got it. Let me know if you need further assistance or if you would like to dive into any other topic. I'm here to help. So nice. Okay, so let me give you the source and start and goal configurations. Let's see what it says. There's an interaction going on in language. Great. Please provide the initial and goal configuration and I'll run the algorithm accordingly. You can share the configuration as 3 by 3 grid or as list of numbers with 0 representing blank space. Great. So I will give in row measure fashion. Perfect, it says. Please go ahead and provide the initial and goal configuration row measure order as a list of 9 numbers. I'll use them to run, say 1, 2, 3, 4, blank, 5, 6, 7, 8. Is the start node and the goal is okay. Let me execute the code for you, it says. Oh. Here is the solution. 1, 2, 3, 4, blank, 5, 6, 7, 8. After the first move, 5 goes here. Then 8 goes up. Then 7 goes right. Then 6 goes right. Then 4 comes down. Then 6 goes up. Then finally this. So did it have to take so many steps? After 14 moves, it has got the final path. Is this the optimal path? Yeah. Okay. But it said I'm running A star. A star is supposed to be optimal. Oh, the path I provided is already optimal with the least number of moves. The A star algorithm guarantees that the solution found is the one with the minimum number of moves because it uses a heuristic, in this case, the Manhattan distance, to explore the most promising states first. So the path I showed you is indeed the solution with the fewest moves. If you have any other question and would like more details, feel free to ask. Okay, so ChatGPT solves this for you. Now, I would like to suggest a project for the class. For the lab, you will finally, when you finish the course, theory plus lab, you will have to demonstrate a project. Okay. The project typically requires you to read one paper and implement it with some value addition from your side. Now, one thing I would like to suggest, I don't know if this has been done before, is you collect lots of these episodes of A star solving. Start node and a goal node, collect many such episodes, and then through machine learning, discover the heuristic. Discover the heuristic. What is the heuristic the algorithm is using? Okay, so if it is Manhattan heuristic, let the ML algorithm come back and say it is Manhattan heuristic. If it is display style, display styles. Okay, some groups in the class can think of solving this problem of heuristic discovery by taking this as data and training a machine learning model. Challenging problem. And I don't know if this has been done. Okay. Another thing we'll have to do in the lab is a probabilistic A star algorithm. With some probability, we'll pick up the least cost F node, least F value node. And with probability alpha minus 1 minus alpha, you will randomly pick a node with uniform probability. Okay. And see what this probabilistic algorithm is giving you. Can you give a probabilistic guarantee on the optimality of the paths? With probability function of alpha, the path is guaranteed to be optimal. This is a theoretical work. Okay, just 1 minute. Arnav, can you write down these two problems? Okay, let me dictate these two problems. And the lab TAs, undergraduates, I think Soham is here. Dion is also here. Dion, you're also here. So can you gather all the data, episodic data of this 8 puzzle problem? Make the data available to the class for heuristic discovery. Now please do this. Let's see who solves it. We know it is Manhattan distance. Let the algorithm discover. Okay, so please write down this statement and make it available on Teams and Moodle. And the probabilistic question is I'll come to you. With probability alpha, the least F value node from the open list is picked up for expansion. And with probability 1 minus alpha, a node is randomly picked up for expansion. Uniform probability. Give a probabilistic guarantee for the optimality of the path found. Give a probabilistic guarantee for the optimality of the path found. What is the probability that the path found will be optimal in terms of alpha? So this is not an A star algorithm now. It is a probabilistic A algorithm. It is not A star now. It is a probabilistic A algorithm. With probability alpha, you choose least F value. Let the heuristic remain H less than H star. So, okay, you are saying that even if you pick up a node probabilistically, ultimately you'll discover the optimal path. Oh, that I need a proof for that. Okay, so now, let's proceed and establish the intuition that better heuristic performs better. Now we have to first rigorously define what is better. Okay, what does better heuristic mean? So this is the theorem. Again, please look at the proofs. Okay, on the slide, I'll have to read through them. All the steps are quite clearly given. Theorem: a version A2 star of A star that has a better heuristic than another version A1 star of A star performs at least as well as A1 star. Okay, so meaning of better, A2 star and A1 star both are versions of A star. Okay, the meaning of better means that H2n is strictly greater than H1n for all n. So H2n is closer to H star than H1. That is the meaning of better heuristic. Okay, and meaning of as well as A1 star will expand at least all the nodes of A2 star. Okay, so A2 star will expand less number of nodes than A1 star. So this, of course, you'll have to verify in the lab that Manhattan heuristic performs better than display style heuristic. So display style heuristic will expand all the nodes that Manhattan heuristic expand and will expand more. Okay, so but we make a conservative statement that A1 star will perform at least as well as A2 star. So A1 star expands at least all the nodes of A2 star. So let's look at the proof. The proof is by induction. Okay, on the search tree of A2 star. So we have to note that though we have a search graph, okay, it is a directed graph, and nodes can have more than one parent. But ultimately, when A star terminates, it carves out a tree out of G, out of the graph. Okay, because every node has a single parent, and there is a start node. Now, the proof makes use of induction on the depth K of the search tree of A2 star. We want to show that A1 star cannot terminate without expanding all the nodes that A2 star has expanded. Okay, so it will expand at least all the nodes that A2 star has expanded. For K equal to 0, the statement is true since the start node is expanded by both A2 star and A1 star. Now, suppose A1 star terminates without expanding a node n at depth K plus 1 of A2 star search tree. The hypothesis is that is that up to depth K, all the nodes of A2 star are expanded by A1 star also, up to depth K of A2 star search tree. Since A1 star has seen all the parents of n seen by A2 star, G1n must be less than or equal to G2n. Okay. Now I give a 3-slide proof of why G1 n k plus 1 will be less than or equal to G2 n k plus 1. This is a 3-slide proof in 2 cases. This is not exactly there in Niels J. Nielsen. Okay, so it will be helpful for you to look at these slides. Now comes the proof by contradiction. Since A1 star has terminated without expanding n, F1n must be greater than or equal to F star S. F1n must be greater than or equal to F star S. Any node whose F value is strictly less than F star S has to be expanded. Okay. Since A2 star has expanded n, F2n must be less than or equal to F star S. So from 1, 2, and 3, we find 1, what is 1? 1 is this inequality. G1n is less than or equal to G2n. What is n? N is a node at a depth of k plus 1 of A2 star search tree. So 1 was that. Then 2 is F1n is greater than or equal to F star S, because n has not been expanded by A1 star. Okay, if A1 star terminates without expanding a node on the open list, its value cannot be less than F star S, strictly less than F star S. And since A2 star has expanded n, then F2n must be less than or equal to F star S. Okay, I strongly suggest that these inequalities you are comfortable with. So from 1, 2, and 3, we have to come to the conclusion that H1n is greater than or equal to H2n. Okay, which is a contradiction, because we said that H1n is strictly less than H2n for all n. Okay, now the non-trivial part of the proof is this. G1 n k plus 1 is less than or equal to G2 n k plus 1. This is a non-trivial part. Okay, and I'm just repeating once only that this proof is not given in Niels J. Nielsen, the principles of AI, from where this A star topic is majorly being covered. Okay, so this means that A1 star before termination has to expand all the nodes that A2 star has. This you do verify in the lab in your implementation of A star. Okay. So now we are more or less done with A star. Well, two, 3 things remain. One is discussion on monotone restriction with an example. Why is it that if a node comes again, which has gone to the closed list, its parent pointer and all the grandchildren's parent pointer have to be changed? Why is it so? I'll give an example. The example is there in the Principles of AI, that book also. And the there are many variations of A star algorithm. There are famous algorithms like island search, for example. Okay, then AO star, which is used for game tree search. So there is this game of tic-tac-toe, which makes use of AO star and or star. Okay, and some important concept like alpha beta pruning is used there. This also you will implement in the lab for the game of tic-tac-toe. Okay, so those variations will come, and but the major thing which has been covered is the A star algorithm. Okay. Now I'd like to change gear and take you to another approach to artificial intelligence. Okay, and from there proceed to some building blocks of that approach. Okay, so we were discussing some foundational points, and in the remaining 10 minutes or so, we would like to say that there are these foundational limits on computation. One is computability, the other is complexity. Even if you can compute some function, it may have prohibitive complexity. It may require exponential amount of space and time. Exponential in what? Exponential in the length of the input. For example, in traveling salesman problem, we know that as the number of cities increases, the time taken to find out the least cost circuit for the traveling salesman also increases exponentially. Okay. So even if something is computable, it can have exponential complexity. Now, there is this Gödel theorem, which has also been found to be very important for AI. The theorem somewhat informally says that a sufficiently powerful formal system cannot be both complete and consistent. When we do logic, AI logic, I understand you have done a course on logic before. You are familiar with completeness, soundness, and so on. But we look at it from AI point of view. And in the lab, you will implement an automatic theorem prover. Okay? Automatic theorem prover for logic, for formal system. A sufficiently powerful formal system cannot be both complete and consistent. This means that at least as powerful as to be able to capture what is called Peano's arithmetic. Sets limits to automation of reasoning. There is a history behind it. So there was a point of time, I think in 1920s, 30s, in that period, that people thought that all the theorems of mathematics can be discovered automatically, okay, by a sufficiently powerful theorem prover. Now, then came Gödel's theorem, which says that a theorem prover which is internally consistent, okay, cannot be complete. That means there will always be theorems which are not provable within the machinery of the theorem prover. There will always be theorems by the machine for a sufficiently powerful system. Okay, so for very toy logic, extremely toy constrained logic, this is not the case. But sufficiently powerful logic, this is the case. Second order logic, for example, is incomplete. Okay, so those things we'll discuss in the set formal systems. Then limits on in terms of time and space, there is NP complete and there are NP complete and NP hard problems. Artificial intelligence is full of such NP complete and NP hard problems. Okay, so for example, let me give you a problem from natural language processing. You cannot write an efficient program which will decide, okay, if a sentence is grammatically correct, if the sentence has ambiguous words. Okay, so solving both words and disambiguation and parsing is an NP hard problem. Okay, is this sentence grammatically correct? And the sentence has words with multiple meanings. Okay, this was proved in 1990s. Okay, that this is a complex problem. So you see, so deciding if a sentence is grammatically correct where the words have multiple meanings has inherent complexity in terms of computation. And then vertex cover problem and so on, which are NP hard. Their corresponding AI problems exist. Then there are two broad divisions of theoretical computer science. Theory A is concerned with algorithms and complexity. Theory B is concerned with formal systems and logic. And AI has been called what is called the forcing function for computer science. AI, for example, time sharing system in operating system came inspired by artificial intelligence because the machine gives the illusion of attending simultaneously many demands. Okay, as if the machine is talking to multiple people. Compilers, it raises the level of machine for better man-machine interface. Okay, and you don't have to know machine language because of the compilers, programming language compilers. And this really arose from natural language processing. And NLP in turn is called the forcing function for AI. So you need many inputs from many disciplines for artificial intelligence. So at this point of time, one may come back. If I do AI, will I become a jack of all trade and master of none? Okay, I'll do a bit of philosophy, I'll do a bit of coding, I'll do a bit of physics, a bit of information theory, a bit of logic. Will I become a jack of all trades and master of none? No, the answer is you will become a master of AI. And I do not care whether you are a jack of all trades. Okay, master of AI is fine. Then we come to this very important distinction between symbolic AI and connectionist AI. Symbolic AI is Turing machine-based, programming-based artificial intelligence. And connectionist AI is what is happening today, deep learning-based artificial intelligence, neural network-based AI. So connectionist AI is contrasted with symbolic AI. Symbolic AI is based on physical symbol system hypothesis. I don't know how many of you reflected on a few hypotheses that we discussed in the last class. Charge Turing hypothesis, physical symbol system hypothesis. For intelligence to emerge, you don't have to do anything other than manipulate symbols. The symbols are mindless. The machine which manipulates the symbols is also mindless. But lo and behold, the whole thing behaves intelligently. Okay, so this is physical symbol system hypothesis. Every intelligent system can be constructed by storing and processing symbols, and nothing more is required. Symbolic AI has a bearing on the models of computation such as Turing machine, von Neumann machine, and lambda calculus. These are proven to be equivalent systems. Turing machine and von Neumann machine. In Turing machine, we have a processing head, which is a finite state machine, and there is an infinite memory. And von Neumann machine, there is a connection between CPU and the main memory, address bus, for example, and the data bus. And however, symbolic AI has been found to be limited. A large number of computations and information process tasks that living beings are comfortable with are not performed well by computers. The difference between brain computation in living beings and Turing machine computation. Brain computation is excellent in pattern recognition. Turing machine-based computation is very good in numerical processing. And human beings are not good in numerical computation. Brain computation is learning oriented. Turing machines are programming oriented. You have to give explicit instruction. Brain is distributed and parallel processing. It is known that visual processing happens at the back of the brain. Auditory processing happens on two sides of the brain above the ear. Music, mathematics, these are higher brain functions. Okay, controlling the breath, controlling the blood flow, the actions which are critical for survival, they happen at the lower brain. Okay, very well concealed, very well protected by the hard skeleton we have, because nothing should endanger those activities. Okay, maybe we can do without music, without maths, but without breathing, without blood flow, no maths, no music can happen. Okay, so it is parallel and distributed processing. It is also known that brain has huge amount of resilience. If a part of the brain gets damaged, other parts take over that function. And then finally, brain is content addressable, whereas Turing machine is location addressable. So we'll discuss these foundational things a bit more in the next class. So we'll stop today and I'll see you in the lab.